Hi, I'm Rochelle Crosby Watson, and welcome to our Muscle Physiology Frog Lab. In this lab video, we will learn how to experimentally measure muscle force in an isolated muscle prep. We will measure concentric force from the gastrocnemius muscle. Remember that concentric contraction is a shortening contraction in which there is a decrease in muscle length. The muscle will be dissected from the northern leopard frog, then electrically stimulated to cause it to contract. We can see all of the molecular lessons from excitation-contraction coupling in real life as we analyze muscle properties in response to electrical stimulation. First, the skin is removed to expose the underlying muscles. The sciatic nerve, which innervates the muscle of the hind legs, will be tied off and isolated. The gastrocnemius muscle, scientists sometimes refer to this as the gastroc, will be tied off and isolated. Once the other tissues have been sufficiently removed, we will cut the femur and the tibiofibula to dissociate the muscle from the hind leg entirely. We will clamp down the femur to immobilize the muscle. The string is run over a pulley and then tied onto the blade of a force transducer. The sciatic nerve is gently placed on a stimulating electrode, which will drive the current into the sciatic nerve. Using a computer program, we can stimulate the sciatic nerve and watch as the muscle contracts. The force transducer will detect the stretch and measure the amount of force necessary to cause this deflection. We can measure several variables of muscle contraction, including the speed of contraction, the force of contraction, and fatigue. Here is an example of the classic muscle twitch. We are delivering a single stimulus, which causes a single unified muscle contraction and subsequent relaxation. The green line at the bottom is a readout of the electrical current being applied to the isolated muscle. Each spike indicates a single pulse. The red line on the top measures muscle tension as detected by the force transducer. These readings are both made in real time to produce the electromyograph. The force is plotted as a function of time for a single twitch, as shown here. We can also measure the latency, which is the time delay between stimulus and the initiation of muscle contraction. So what causes the latent period? The latent period is the time required for all of the molecular machinery that we've discussed in our course to begin working. There is time needed for the propagation of the action potential, release of calcium stores from the sarcoplasmic reticulum, and cross-bridge cycling. Here we can observe tetanic contraction. Notice that the stimulation is much more rapid. These green lines indicate individual shocks that are delivered rapidly in succession. What causes these sustained, strong contractions? All of the calcium stores are being released into the cytoplasm, which allows for maximal cross bridges to be formed. So, studies on force production and EC coupling can reveal a lot of information about the muscle health. We can obtain measures like maximum force production, speed of contraction, and fatigue, which is a pattern of decreased force production across several repeated stimulations. What's really great about these physiological experiments is that we can obtain the data in real time. Importantly, the effectiveness of various therapeutics can be evaluated using these physiological outcome measures, like the ones that we discussed in this video, to determine whether a genetic or a pharmacological intervention improves muscle strength in Duchenne muscular dystrophy.